So we've already seen for the inverse for the sine, the arc sine, also known as the sine inverse, had to be constrained so that it was actually a function. And so it had a domain of -1 to 1 and a range of pi/2 to -pi/2. And then it's got this brief wave in between there. So it has endpoints there and here, goes to the origin, and it arcs like this. Ooh, that wasn't a very good one. Slightly better. All right, so that's the arc sine. Now, to get the domain and range of the arc tangent and the arc cosine, let's just think about the cosine function for a second. So cosine of x, we know has a peak on the axis here, and then it drops down, and then it comes back up. Same thing on this side, it drops down, and it comes back up. And it's going to reach its peak again, making a full period here at 2 pi. And then in between, it's going to reach its minimum at pi. And then it's going to have a 0 here at pi/2, -pi/2, and a bottom here at -pi. Okay, so that's the graph of the cosine. You should be pretty familiar with that for now and those special points there. So then I need to decide what part of this wave am I going to use so that I keep it 1 to 1, so that when I flip x with y, it becomes a function and passes the vertical line test. So whipping out the eraser right here, I know that if I go past the turning point, then I have a problem. So this part of the curve is a problem, so I have to erase it. So this is nice. This is a good part here. And then once I get to that next turning point, after that's a problem. So I have to erase that too. So that is the chunk of the cosine that we use for the inverse function. So let's try to graph the inverse. So f of x equals the arc cosine, also known as cosine inverse or inverse cosine. And so what do I know about it? Well, instead of having the point 0, 1, it should have the point 1, 0. So let's make a little table over here for the inverse x f inverse. So this had 0, 1, we're going to have 1, 0. This one had pi/2, 0, so this one should have 0, pi/2. And then this one had pi -1, so this should have -1 pi. So here we had a range of 1 to -1. That becomes the domain of this function. So -1 to 1. Here we had a domain from 0 to pi. That becomes the range of this one from 0 to pi. And I guess I better move that down a little. Oh, no, I want all of you. Darn it. There we go. So extend that up a bit. So let's say pi is up here. Pi/2 is going to be right in the middle. So I should have the point 1, 0. I should have the point 0, pi/2. And I should have the point -1 pi. Just going to put me up there. And then I'm going to arc over to that. So it should look like that right there. And again, if I kind of drew it on top of the one above here, that's pi/2. 1 would be about here. Pi would be way up here-ish. Pi/2 is going to be over there. So, and then -1 would be somewhere over here. So my scale's a little bit off on this one, but it should look something like this. And those two should be inverses. They should be symmetric about the line y = x. So let's take a look at that on a graphing calculator. So y, let's call it f of x. Now let's call it y. Cosine of x. And then we're going to look at the inverse, y equals the arc cosine of x. And then compare that to the line y equals x. And so we should see again, remember this function we had to cut off right here, and then again down there. And so that chunk of the black curve should look symmetric to the line y equals x to this red curve here, the inverse function. All right, so can you see that symmetry in there? If we go to erase the rest of the black part. All right, tangents. Let's think about the tangent for a minute. Y equals the tangent of x. Remember, tangent comes from the sine of x over the cosine of x. That's not helpful for the inverse, but I like to put that there when I'm thinking about the graph of the tangent. Out of the way, zoom. Come on, I need my pen. So axis, axis. So since the sine is 0 at the origin, the tangent is also 0 at the origin. The cosine is 0 at pi over 2, which means I'm going to have a vertical asymptote there. Same thing over here at negative pi over 2. And then otherwise, the tangent rises up on that side and drops down on that side. And then it repeats that chunk over and over again. So over here at pi and 3 pi over 2, another asymptote. And it just does the same old thing in between, not crossing those vertical asymptotes. And then if I consider the idea of the horizontal line test for an inverse function, oops, let's make it red, there we go. It's going to fail if I include any of those other chunks of the tangent. So I don't want that chunk, I don't want the chunk over there. So basically I can just keep this chunk in the middle there. So let's get rid of some of that and erase this chunk. So if I get rid of that chunk right there, then I'm good. This chunk right here that I've left behind, if I consider that horizontal line again, for any value of y for this horizontal line, I'm hitting this function only once. So now this chunk of the cosine, the tangent, excuse me, is 1 to 1. So if I just consider the tangent from negative pi over 2 to pi over 2, then I have a 1 to 1 function. So then now if I want to talk about the inverse of the tangent, the arc tangent, what do I know about it? Well, here, again, the inverse function switches x and y, so the domain and range switch. So here I had, with the original, a domain of negative pi over 2 to pi over 2, not including the endpoints. And I had a range of all y values, so negative infinity to infinity. For the inverse function, those are going to switch. So this is going to have a domain that is going to be from negative infinity to infinity, but the output is only between negative pi over 2 and pi over 2. So if I were to graph that over here, let's move that line out of the way. Oh, whoa, how did that happen? Oh, interesting. I don't know what button I just hit. That was cool. All right, so here, again, my range, I can't go below negative pi over 2 or above pi over 2, so those vertical asymptotes turn into horizontal asymptotes. So I'm going to have a horizontal asymptote, say it's up here, y equals pi over 2, and down here, y equals negative pi over 2. Otherwise, the x's go in each direction. So it's 0, 0, we're still going to have that point. And then this function is going to rise up like that to its asymptote, can't cross it, and it's going to drop down to its asymptote on the other side over there. So that's what the inverse tangent, the arc tangent, is going to look like. Graph that on the calculator. Y equals tangent of x versus y equals the arc tan of x. And so we can see that purple function there is the one I'm curious about. Let's turn off the tangent for a second. Turn off the line y equals x, and then look at those horizontal asymptotes, y equals pi over 2, for example. And so what I should see as I move out to the right, it's going to get closer and closer to that, but it's never going to touch it, can't cross it. Okay. Some functions can cross horizontal asymptotes. This one cannot because of its origin, and its origin was the tangent, and those vertical asymptotes on the tangent, like x equals pi over 2, are uncrossable because there is 0 in the denominator, and we can't divide by 0 in math. It's illegal, it doesn't work. Summary. So the important thing about these inverse functions are the angles that they output. So we've got the arc sine of x, and its range is really the most important part here, the angles that it outputs. So angle range is from negative pi over 2 to pi over 2, and we do get the endpoints. The arc cosine has a range from 0 to pi. So those are the angles it will output. And then the arc tangent doesn't include the endpoints, but it is like the sine from pi over 2 to negative pi over 2 for the angles. So anytime I have a problem where I'm doing an inverse function, if I need an angle outside of these ranges right here for the output, then I have to do a little circle symmetry work to figure out what that angle might be. All right, now let's play a little more.